Morning everyone. Today my concept video topic is about the geometric connections of two kinds of complex numbers. I am Naresh from ECE A section. This is the PPT of CSF subject. Let's get into the topic. The hyperbolic complex numbers of an elliptic complex number. The Clifford, a British mathematician, introduced J, a new kind of imaginary unit which satisfies J square equals to 1 and J not equals to plus or minus 1 and J star equals to minus J. Here J is named as hyperbolic imaginary unit and J star is the complex conjugate of J. So J is a hyperbolic imaginary unit and the J star is termed as the complex of conjugate of the that hyperbolic imaginary unit, and therefore h of x j y can be considered as two-dimensional hyperbolic complex plane. The linear equation A is equals to x plus jy. It is named hyperbolic complex numbers where real number x and y are real and the imaginary part of the complex number is less a number respectively. In order to connect hyperbolic complex space-time with physical space-time, we set xct, yr if c is light velocity and t is time, then h of ct, jr can be considered as two-dimensional hyperbolic complex spacetime. The hyperbolic complex number is and its complex conjugate can be expressed as a is equals to ct plus jr and a star is equals to ct minus jr. The modulus of hyperbolic complex number is shown as r equals to a mod of a suffix m is equals to under root of mod of a star into a, that is equals to under root of mod of c square t square minus r square. This is the third equation, and c square t square minus r square equals to plus or minus 1. So that the equation 5 describes two couples of hyperbolic in the hyperbolic complex plane. Equation 4 divides the hyperbolic complex plane into four regions, and it is the zero modulus point and the asymptote of equation 5 when r naught. So this is the equation 5. C square t square minus r square is equals to 1 plus 1. In the hyperbolic complex plane, regions that satisfy RCT and the time-like regions where the unit modulus corresponds to a positive sign of phi, and it is a couple of hyperbolas and with the real axis ct and the symmetry axis. The regions that satisfy r modulus ct and the space-like regions where the unit modulus corresponds to the negative sign of phi, and it is couple of hyperbolas with the imaginary axis jr has the symmetric axis. Zero modulus point r naught are the light-like region. So the zero modulus is where r naught is the region which is very light, and obviously two-dimensional hyperbolic complex plane correspond to Minkowski space, therefore can be named as hyperbolic Minkowski space. It has logical connections with the properties of hyperbolic complex numbers. The imaginary unit I of I square equals to minus 1 into I star equals to minus I is named elliptical imaginary unit. elliptical complex number and its complex conjugate can be expressed as B is equals to Ct dash plus Ir dash, which is the sixth equation, and B star is the Ct star minus Ir dash is the sixth B equation. It is modulus of L is equals to modulus of B in suffix M is equals to under root of B star into B. B is the complex conjugate of B. B star is the complex conjugate of B, and which is equals to under root of C square T dash square plus R dash square, which is the equation 7, when C square T dash square plus R dash square is equals to 1, the unit circle of an elliptical complex plane. This 8th equation shows the circle elliptical complex plane. The second topic of this topic is the geometric connections of two kinds of complex numbers. The hyperbolic complex plane h of ct minus jr corresponds to two-dimensional complex Minkowski geometry. The elliptic complex plane E of ct dash minus I comma ir dash corresponds to two-dimensional complex Euclid geometry with the utilization of Jordan-Mason function. Corresponding geometry relationships of two kinds of functions of a complex variable and complex planes can be established by making Jr the imaginary axis of hyperbolic complex plane h of ct minus jr and IRC the imaginary axis of elliptical complex plane E of ct dash minus comma ir dash coincides, and by settling real axis and the imaginary axis orthogonal unit modulus correspondence of two kinds of complex plane can be figured out with the help of two-dimensional realness. So the two complex plane will be figured out by the two-dimensional real axis shown in the figure. So that j omega is equals to I into r by r dash. R is equals to r dash c square t square plus r dash square by ct dash. Ct is equals to c square t dash square plus r dash square by ct dash. In summary, the modulus r of a hyperbola space-time point x of ct minus jr in the hyperbolic complex plane h of ct minus ct comma jr is equated with the modulus L of a tangent circle space-time point y of ct dash minus ir dash in the elliptical complex plane, and the space-time conjugate x of ct comma jr and y of ct dash comma ir dash satisfies, that is the arbitrary space-time point x of ct comma jr in the time-like region of a hyperbola. It is similar to the previous one and correspond to the space-time say y of ct dash minus ir dash in the elliptical complex plane is e of ct minus ir dash comma ir dash, where the hyperbolic complex field added to the light-like region is called generalized field. In this paper, we showed that discussing mathematical and physical problems in generalized field will be fruitful for both such fields. Thank you.